Hey everyone, can you hear me okay in the back? Good? Awesome. So, like you said, I'm Kevin Horecka. I currently am the lead data scientist at Walmart Technology that's down the road. But in a lot of my free time, I work with Austin Pets Alive and American Pets Alive, which are down, what direction? Cesar Chavez. And I've been volunteering there since about 2011 and have noticed all sorts of different opportunities to try to use different advanced technologies that they aren't aware of, and even actually basic technologies that they're not aware of, in order to help them with their mission, which is to save all pets that are being needlessly killed. So there's a lot that goes into, their definition, their mission, those sorts of things. Oh, is this thing not working? Okay. I can't take that off. There's a lot of things that go into this mission, and I don't have time, unfortunately, to tell you all about what they're doing and all the cool things that they're doing. So instead, what I decided I'd do is pick out the three sort of most advanced case studies that I've done with them to apply these advanced technologies to help them with their mission, which is effectively to save as many animals as they can. So there are four takeaways rather, that I want you to sort of get out of this talk, and none of them have to do with the details of the case study. I think there's a lot of cool engineering and technology that you're going to see scattered throughout this talk. But actually, my pitch to you has nothing to do with the technology. It has to do with your skills. So most of the people in this room probably do have some interesting skills. We all have very varied skills. And the sort of thing I want to emphasize out of this talk is that you have skills that you can use to help nonprofits. And that is probably the most satisfying thing you could do with your free time, and I've absolutely loved doing it over the past 8 years or so. So the challenge here is that the nonprofits really have no idea anything about technology. Like, we're talking, they don't know Google Forms exists, and so like they need you to go to them. They can't advertise for what they need because they don't know what they need because they don't know what's possible. So that's a huge part. And what comes along with that is that helping them is actually very hard, and it often requires you to spend a lot of time with them trying to understand them because they can't spend time with you understanding you. They're already strapped for resources and really need you to work on their terms, not the other way around, which I think is why engineering isn't as pervasive in a lot of nonprofits as it could be. You're going to find the moment you go to basically any nonprofit that doesn't already have engineering people, there are a million cool problems that you can solve for them. And the reason I think that you're not seeing more of that in sort of the public eye is simply because they're so busy they can't reach out. That makes sort of it cool that you can get in there and immediately make impact. So that's an exciting thing to be able to do for an organization. Literally give them the simplest technology. You're just like going to be like, how could they not know that this exists? But the thing that you give them is going to be incredibly valuable. So it's simultaneously very hard to work with and very easy to solve their problems for the most part. But lastly, because they don't have sort of domain experts in engineering, you really need to be careful what technologies you give them for a variety of reasons we don't have time to go over here. One of the reasons I'm going to emphasize, though, when it comes to really advanced technologies is that they don't understand a lot about like data science and modeling, and they may not think of the unethical uses of models. So for instance, you come up with a really good model that predicts some aspect of their process. They may have competitor organizations that if you make that model public, will use that to do the opposite of their mission, because all of these models are double-edged swords, depending on who you're talking to. So this is really what I want you to get out of the talk. The details that I'm going to go into I think are really interesting, and I hope you enjoy them. But I think there's a lot more opportunity for us as engineers to help out these nonprofits. If you're specifically interested in animal sheltering, that link there, which hopefully you can see later, links to an article that I published a week or two ago on all of the problems that animal shelters are facing, just to kind of stimulate ideas on if you know any technologies that might apply to those problems, you might be able to participate in that setting. Okay, so this talk we're going to go over 3 case studies, one on a disease called parvo and some of the health economics work that I've done in that space, one on distemper and some disease simulation spread. If you've been to our Data on Tap events, you've probably seen a lot of this content. You won't have seen this third one, which is developing dashboarding and other technologies around KPIs, top-level measurements of success for these shelters, in a way that can solve issues with tracking how well animal shelters are doing, because believe it or not, we don't actually know how many animals are being saved or not in the US. I'm also going to try to do this thing where I'm going to put any tools that I use, sort of their logos, up in that corner. So if you're curious how I did something, you can kind of look up into that corner and get a sense of what tools were being used. So for parvo, the goal here with parvo is parvo is this highly deadly infectious disease. It's an intestinal virus. It kills over 90% of the animals that it infects. If you treat it, you can save 90% of them, so totally flip it on its head. It is really only killable by bleach, and unfortunately lives in the environment for over a year. So if a dog with parvo goes to a dog park, then that dog park has parvo for at least a year, assuming no other dogs go there. And you're not going to bleach the grass, so it just is. And there are places that they actually will go through and completely tabula rasa the field, but that's not as common. So it's ubiquitous in the environment. It'll end up killing the animal from dehydration and secondary infections, so you can just treat it by giving them fluids and antibiotics. So we're already doing this. And it'll resolve within a week or two, and it's kind of like chickenpox. You won't get it again. If you have an animal, you don't need to worry about this because you probably got them vaccinated. Hopefully you got them vaccinated. If they're vaccinated for it, they're good to go. So these aren't risks for any dogs except for ones that haven't been owned before and therefore haven't been vaccinated. So the things that we'd like to be able to do in this space are convince others to treat this disease, because believe it or not, most people just kill them the moment that they have it. And sorry if this is a little hard to read. None of the stuff in here is super important. We want to be able to optimize the treatment so that people can not just treat it, but treat it cheaply. And we want to save the 10% of animals that we're not saving within this space. The key strategy here, as you can imagine from my pitch at the beginning, is that we've really got to get into the shelters, understand the stakeholders' needs, and save them time with tools so that then we can get the data we need to actually try to answer these questions, because they don't have that data, and they don't have the capability to collect it up front. And so the strategy that I used in this project, which spanned many years, was to basically try to save them time so that I could get the things I needed to try to work on these problems. So the first step in saving time for me was to build them some tools. I built them end-of-shift reports, dashboards, some document scanning, literally just show them how to use Google Drive to scan documents, process documentation, so a wiki that describes what they need to do for things. Then once I provided that value, I asked them for some follow-up help, try to get things like how many animals are coming through with the disease, how many volunteers are being used to treat them, because actually Austin Pets Alive has the largest parvo treatment ICU in the world. We treat more animals per year than were used to validate that the test for parvo works. So we're talking order of magnitude more animals than anyone else sees with parvo in the entire world. So how long are the shifts taking? What are they actually treating them? How are the vets behaving towards these animals? What are the demographics and outcomes? And then you can use this data to provide more value that then lets you get into this cycle of sort of success, where you're starting to give them insights, give the shelter insights that they can take home and use, things like dashboards and analytics, things like predicting outcomes, analysis of risks, which I'll show you a few of these things, and some demographic distribution information, as well as things like resource allocation, which they don't know, how much time and money is going into these things a lot of time, and that's a really critical fact if you're going to try and pitch other organizations to do the same things that they're doing. So starting off, take the Google strategy, because they already used a lot of Google tools, Gmail and Google Groups. Give them things like better data tracking, easier printing of their sheets and dashboards, give them all these tools, teach them to use the tools on their terms, so don't sort of force the tools in. I actually made probably double this amount of tools and the other half failed because they just weren't working for them. So sometimes you've got to kind of throw a lot of different options at them and see which ones work out best for them. And then once you've done that, you've gotten this sort of upfront investment in these two fields, which then allows you to answer questions to try to get other people to actually treat these diseases. So the first question that we wanted to ask was just how much does it cost? Turns out it costs $56, and you can see that that's the mean, the median's to the left of that, and that cost is primarily driven by the cost of medications. And so larger dogs need more medication because medication is dosed by weight, and so the result was that we can give advice to other shelters who want to treat this that you should start off with your lighter weight dogs. Lighter weight dogs have a higher risk of dying, but you can kind of pick and choose your populations if you need to for cost reasons, and understand your expectation should be $56. Then you can continue and say, well, okay, within that population, what are the expensive things we do? What are the cheap things we do? Those are the medications that they give on the top. That big sharp bar there is actually an anti-nausea medication. It turns out you can actually treat parvo without that. So if you eliminate that bar, you can cut your costs in half, because that bar actually is bigger than the sum of all the other bars. And so that's another piece of advice you can give to other organizations that we didn't know up front. We knew it was expensive. We didn't know it was that expensive, and that if you take it away, you half your costs. Another thing to note is that really lightweight animals have a really poor chance of survival up front, and so shelters may need to adapt their practices as APA has for those animals. We actually place IVs immediately upon arrival in those animals to increase their chances, which is something we've started in the past year or so. On the economics front, for the human resources, APA is a largely volunteer-run organization, and so the question was how many volunteer hours are going into these animals as well, because then another organization who wants to treat them needs to get that many volunteers in order to treat that many animals. It turns out it takes about 9 volunteer hours to treat one animal, so that's this plot on the top is number of animals versus number of hours, and you get a roughly linear trend. It fits a little bit better if you do like a log trend, which actually is kind of a nice thing because that means they're probably being more efficient the more animals there are. But then if you look at things like how we're load balancing staff, which is this bottom plot, so it's that top plot, but then you add how many people were on shift at a given time, you'd hope that this thing would be flat, which would mean that you're optimizing the number of people on the shift. That is not the case, and so that means that we actually probably need more volunteers at APA. So if you want to learn to give injections and do stuff like that, you should probably reach out and volunteer at the Parvo ICU. So that was it on the health economics front. There's a ton more stuff I'd love to tell you about, but I've got 2 other case studies to get to, so we're going to move on. When it comes to things like how to save that last 10%, we really want to address some of these reasons why we think the treatment might fail. So we think that maybe they're arriving too late at the shelter, maybe they're catching other diseases like the one I'm going to talk about in the second case study. The treatment just might not be effective for some reason. We haven't really studied the treatment enough to know why it might fail. And then we also know that there's only volunteers in there for a little less than 50% of the time throughout the day, because there's a lot of nighttime where there's no volunteer there, and the really critical animals will crash during that time, meaning that their vitals just start to go terrible and then they'll die while no one's there. And so we have protocols on what to do, and when we're there and that happens, we tend to be able to pull them back. They don't always survive at that point, but they may get like a 50% better chance of surviving at that point. And so being able to detect when that happens and help and intervene would be, I think, a way to increase those numbers. So one of the key things then in trying to get a sense of that is to get a better sense of when they're at risk, what the progression of the disease looks like. These are all sort of unstudied things for the most part. And we do actually have a direct measure of risk. Whenever you go in and treat one of these animals, you pick one of these bottom 4 statuses. They're either bright and responsive, which is a normal puppy, because it's mostly a puppy disease. They're quiet and responsive. They aren't bright, but they're not lethargic or comatose, which are the other 2. And you can look across time for the whole population how this sort of progresses, and you see they sort of come in fairly critical, and then they have a flat period where they're still recovering from the disease, and then they start to improve as a population. So that's sort of the time course we expect. Obviously, there's some variability here because they get to us at different points in time, but even just from this really naive score, you can get a sense of how the disease is progressing across the whole population. You can also see those lines that are going straight up to the top. That top line is deceased. So you can see where they're dying in this plot, which is basically in those first couple days of treatment. So we really need to understand what to do during those first couple days. You can take this a little farther, and this is a fun thing to play with if you're ever doing risk analysis. You can use things like a Cox proportionate hazard model, which is a model that makes some assumptions about the exponential nature of the risk of an event occurring at any given moment in time. And you can actually create a score of risk using a model like this, using a variety of variables. So in this case, we use that score from the previous slide, but also things like what color are their gums, which is a subjective thing. A volunteer goes in there and says, are they pink? Are they pale pink? Are they white? White is bad, means they have very low circulation. Are they throwing up? What's their sex, which turns out to matter? And we found that a couple different times. Still don't really know what's going on with that. And what's their paw temperature? If their paws are cold, they also have bad circulation. And you can throw those things into one of these hazard models by giving it a time series of these variables as they're measured on the treatment charts, which are already being logged every day. And you can then get sort of a regression variable that maps how at risk, given those variables, are they of hitting the critical event of dying. So many of the animals are never going to hit that critical event, but you can still use their data. Some of them will. And when they do, you can sort of look backwards at what the variables look like and create an exponential regression leading up to that event. When you do that, you get the plot like this red and green one over here on the side. The red ones are ones that ended up dying. You can see there's a lot of variability, and they're already higher than the green dogs, which are the ones that survived. These are ones that were matched for how long they stayed in the ICU. So that's going to create a lot of biases, actually. So not the best canonical comparison. And then you can look at the relative importance of those different variables so that people can take that into account in trying to understand this score. You can also take all of that data and that score and try to make different supervised modeling approaches to say, are they going to die or not? That's really what we want to know, right? At any given time point, are they going to die? Because if the answer is yes, that means they are going to die within the context of the treatment we're giving them. And so we can maybe give them a new treatment. We can do something experimental. If you've heard of fecal transplants in humans, that's a kind of popular thing to pop up in the news. That's actually an experimental treatment for parvo as well. You literally get the poop from another dog, put it in a blender, put it in the other dog. And apparently that works really well. I'm not a vet, so I couldn't tell you why. But doing this problem of prediction is actually, it's interesting, because if you give the model, say, 4 treatments worth of data, which is 2 full days of data, that is enough to do a really good job of predicting the outcome. You can hit nearly 100% within the data set that I have. It's a small data set, so don't trust the results too much. 2 treatments, pretty hard. 1 treatment, virtually impossible. So this is the confusion matrix for 1 treatment. This is the best I was able to do if you take a single treatment and try to predict death from it. And it doesn't matter which treatment, but I did the models with the first treatment because really that's what we want. The moment they come in, we want to assess them once, and then we want to know the answer. Once I built all this stuff, I really wanted to get a sense of how it was working, so I deployed the Cox proportionate hazard model to a little UI that the vets can use and go in and just say, like, I think this dog is not going to make it. Let's see what the model thinks. And I got some feedback from them on whether or not it matched their intuition. Very anecdotal feedback, so not something that I want to trust yet, but we're collecting data all the time to improve these models. Their feedback was actually really positive. They felt like once a dog hit about 30 on this score system, they were pretty critical. Once they hit 100, they were likely not to survive. And then the data actually says once they hit 300, they won't survive. So it gives you a little bit of a sense of the utility that these things could bring. The last bit, which I think is one of my favorite pieces of this and still a work in progress, is doing some computer vision to try to put a low-cost Raspberry Pi camera on these dogs and track their respiration and look for that crashing signal so that you can actually send out an email to get someone to come in and do the crashing protocol on them. And so this is a video of the algorithm that I wrote to do that. It uses a combination of computer vision techniques, PCA, and a couple other things. And you can isolate regions of the body of the animal where respiration motion is occurring. You can then crop the image to that and run your algorithm on it in real time on a Raspberry Pi. So that's a kind of nice potential approach. The reason why this isn't happening right now in the ICU is because I don't have a good data set on sleeping and or crashing animals to validate the model on. So that's the next step that I'm working on right now on this. But a lot of interesting things you can do in this space. I do want to take a moment here at the end of this particular case study to note what would happen if I succeeded in making a model that predicted on the first treatment and then release that model to the world. The vast majority of people, as I mentioned at the beginning of this section, do not treat parvo and in fact kill the animal the moment they even think they have parvo. They don't even have to test positive. If they're showing symptoms, they'll just kill them. And they'll actually often kill all the animals around them too. Sometimes some shelters in the extreme cases will wipe their population. They'll just kill everyone because it's just not worth the risk to them because of how infectious it is. So releasing a model that would allow someone to say, this animal is not going to survive a treatment of parvo, therefore we should kill them, is probably my biggest fear of any model I would ever build, that someone would use my model to decide when to kill something. So I would never release this model right now, even if I got it working. And I think it's an open question in these spaces where there's sort of a desperate need for people to understand what's going on and they're not all unified in their ethics as to when and how you should release these models safely. So that's just something I wanted to bring up because I think it's a complication. Even if you succeed, have you really succeeded? Okay, moving on to number 2. So there's another disease, and it happens a lot in that parvo ICU, called canine distemper. This is oftentimes when I was talking about sort of another disease that kills a parvo dog, this is usually the other disease. Distemper is an airborne virus, so it's very different from parvo. It does not survive out in the environment very long, but it's incredibly infectious within sort of about 20-foot radius around animals. About 15% will survive without treatment, so a little better than parvo, but still not good. It also has the side effect of causing neurological dysfunction for probably several years after, and potentially the rest of their lives after. They'll have really bad twitching. It often prevents them from sleeping, so you have to give them sedatives all the time because they're constantly twitching. And so we really want to prevent them from ever getting this disease more than we want to treat it, because treatment is somewhat effective, 80% survival rate, but even if they survive, they have these long-term side effects. So it does typically occur in these small numbers of populations, and the real issue is when there's an outbreak. So one animal comes in with it, and then suddenly a bunch of animals have it. Once again, your animals are vaccinated for this if you have an animal, so you shouldn't have to worry about this. But within populations that aren't yet vaccinated, it's a real problem. The way that shelters who try to combat this, rather than killing the animals, try to combat it is by having an intake area. It's a hold area, because the vaccine actually takes about 72 hours to become about 90% effective. And once it's effective, you can put the animals in the general population without a whole lot of worry about them spreading the disease. So they create this 72-hour holding area where the animals can be placed temporarily until their vaccination status becomes known, and then they can go out into the population. That seems to work pretty well to prevent these outbreaks. The issue becomes when you have like a rolling outbreak within that intake area, where it just seems to bounce from animal to animal as animals get released, and then as new animals come in, and the new animals catch it immediately. And so they need a way to sort of break these rolling outbreaks that can occur in these intake areas. So that was the main question. There's some complications. There's virtually no data to address things about the spread of this disease. There's really not an inexpensive and reliable test for the disease, so it's not like you can go in and test the animals, see if they have it on intake. It costs a couple $100s to do that, and if you did that on every animal, you wouldn't have an animal shelter. Many of the animals that come in, you don't know if they're vaccinated or not, so most of the animals that come in are getting surrendered by someone. They just drop them off and leave. You don't know if they had vaccines at the beginning. And there are also a lot of other disease, kennel cough, things like that, that look just like distemper in the early phases. So it's really hard to differentiate if it's actually the really dangerous thing that we care about until it's too late. So what we'd like to know is, how do we stop these rolling outbreaks? What kennels within this intake area are the riskiest or not riskiest? Because if we do know the vaccination status of an animal, we can put them in the high-risk kennels because they're less likely to get the disease, and we can kind of spread that risk out across the population. And what changes could we potentially make to these intake areas that they're using in order to prevent the spread of disease in the first place throughout these kennels? So that was what this project, this case study project, is about. The strategy I took, because as you can imagine, I just said there's no data on this, so what am I going to do? Well, in the previous one, I took the long run of trying to generate data, collect data within the environment. This one was a very immediate problem when it came up. There was actually a distemper outbreak at Austin Animal Center, and we were trying to help them with that. And so it was really critical to kind of get some insights early. So what I chose to do instead of waiting for disease or for data collection was I chose to try to come up with a simulation of disease. Now this is very speculative when you do something like this, but luckily there's a lot of research into how airborne diseases work. And so I was able to create the simulation, which I'll show you in a second, improve it by measuring the aggregate statistics that we were getting out of AAC as to how many animals were showing up with signs, how many of them were dying, all of these different probabilities that we really wanted to know, as well as doing lit reviews and things like that to try to pull them out. So make the disease model look more like the disease we're interested in, which is distemper, and then take that model and evaluate the different human strategies the veterinarians and other people are trying to design to modify those intake areas to tell them which one's probably the best, as well as maybe provide some other insights that could be useful for them. And then finally, and this is the work in progress, is train a reinforcement learning system to try to make machine strategies that might be better than the human strategies. So, human strategies have the property of being explainable, which is nice, but they often miss a lot of complexity that could be added in to improve the results. And so if we can give them a machine design strategy that works better, I think they'd be very happy to use it. The sort of mathematical manifestation of this problem is a Markov decision process operating over nodes in a graph. So you can imagine this is sort of the kennel intake area where each of the nodes are a kennel, each of the edges are whether or not that kennel can infect that other kennel. And so this graph generally, if you're talking about a kennel layout, is going to be a planar graph, unless you're like stacking kennels on top of each other, which they do in some, but I made the assumption that they're not going to within this intake area, which they generally don't within the intake area. And then you treat each of these as a node that can contain a state. It can either be empty, have no animal, it can have a deceased animal in it, or it can have an animal with one of the four properties of either being insusceptible to the disease, susceptible to the disease, infected by the disease but not showing symptoms, or symptomatic, so infected and showing symptoms. And then all we need to define how the disease is going to spread throughout these kennels is the probabilities of the transitions between these different states. There are a couple of them that are complicated by the fact that we know that it's an airborne virus, therefore it can spread potentially more than one hop in the graph away. And so the way that I deal with that is by defining a function, a kernel function, that says the probability is this for 1 away, this for 2 away, this for 3 away, et cetera. And then the last complication is the fact that actually animals, as we've said, become immune after 72 hours, and their immune status actually follows a sort of saturation curve. So over time, they become more and more immune, meaning it becomes less and less probable that they become infected. So if you take all that, put it together, which I could have been showing you these while I was telling you that, when you define all of that, you have a description now of a disease. Not necessarily a disease we're talking about, but a disease that can spread throughout an area like this. And then when you simulate it, this is just a disease, a random disease that has random probabilities, you get a behavior kind of like that up at the top. So the different colors are the different states that we're talking about. Blue means that they are susceptible to the infection. Green means they're good to go, they're insusceptible. Yellow means they're infected, but we don't see it. Orange means that they're symptomatic. Black means it's empty, and you'll see a flash of red, which is when one dies. And so you can track these different things over time and look at sort of what the behavior of the disease is over time as a particular population flows flows through a kennel system like that. But as I said, this is for a random disease, so we really want to tune these parameters so it looks more like distemper so that we can actually get some insights into how this disease behaves. And the way that we do that is by first using expert knowledge to fill in what we can. So for instance, it turns out in many of these intake areas, the moment they show symptoms, they get removed. And so we know that the probability of going from symptomatic to empty is 1. It happens instantaneously. They remove them immediately. So there are many of those probabilities within the connectivity of that Markov process that we can describe just by knowing the behavior of our intake area. And then there are a couple like, okay, how should the immunity curve look that we can take from other diseases. So it turns out the distemper immunologically has a lot in common with measles, so we can actually look at the measles immunological curve, compress it into the right time, and get at least an approximation. So there's some guesswork involved in that. Then we gather those aggregate statistics. So how many animals after a month should die within this many animals within this kennel size? What proportion of the animals should be infected within this particular time? And we can take those aggregate statistics and try to tune those parameters to them. Fortunately, we had those aggregate statistics, or rather unfortunately, at AAC because of the outbreak that was going on. So I was able to take sort of after this amount of time, what proportion of the population should have this property, and use that to try to look for probabilities that if you run the simulation for a month, produce those relative proportions of the population. And so you can actually do that, it turns out, directly. I haven't gotten around to doing that direct calculation. There may not be a unique solution, but you can do some like polynomial chains to actually calculate those directly. But you can also more quickly do something like Bayesian optimization, where you just search the parameter space of those probabilities until the result of the simulation fits the aggregate statistics that you're interested in, which is what I ultimately did. If you haven't used this technique, it's a really nice way to do hyperparameter tuning and other things that's a little bit faster than something like a random search cross-validation. Has other uses too. So once you have that, you can start testing those human strategies. So human strategies include things like imagine that you have different rooms where the animals are. So maybe you put them across 4 different rooms, and you isolate the sort of the sections of your graph computationally into those rooms, so that there's no connections between the particular. And here there's 8 rooms, which are each rows. So no connections between rows. Add animals to a particular room until it reaches capacity, but then if it doesn't reach capacity after a day, lock the room for 72 hours. No other animals go in or out of that room. And then if you need to overflow, you can take over the next room, but that's generally ill-advised. So don't add 2 animals from 2 different days to the same room. That's the key insight. This is a strategy the veterinarians designed and have actually tested several times, but they don't really know how well it works. Another strategy which is a little bit more effortful, but has similar properties, is to treat the whole kennel graph like a queue and actually feed animals in at one end and pull them out at the other end. And every time an animal gets pulled out, you shift them all down one kennel. Now, of course, that means you have to clean every kennel every time an animal leaves the system, so you tend to do this in batches. But it's an alternate method of doing this if you can't, say, have 4 different rooms for 4 different periods of time. So both of these different human design strategies have sort of a shared property, which is that space and time are sort of, the changes in space and time for an animal are sort of locked to each other. So if 2 animals come in together, they're likely to be adjacent to each other for the entirety of the duration of their stay, as opposed to what you really don't want to do is have an animal come in 2 days after another animal and then place them next to each other. Because if that first animal was infected and you didn't know it, you've now given it to an animal who's going to stay longer in the system, which allows the disease to persist in the system for much longer than it would have had you kept them apart. So you really also want to avoid changing adjacency, which has the property here. None of the animals are ever next to anyone except who they came in with. So when you run the simulation on those different human design strategies, you get results that look a bit like this. The basic takeaway is that that room locking strategy works really well, and it is the best strategy, but it artificially restricts throughput. So as you can imagine, if all the rooms are full, you just can't take new animals. And the amount of animals that make it through in the snaking case is actually greater than the amount that you can make it in that, because on any given day you're restricting the graph to a subgraph. And so if you have a high variance on that day where you happen to take in more animals and you exceed the capacity of that subgraph, then those animals can't be intaked. And so you've restricted the throughput on that day. And in aggregate over time across 30 days, that means you take in fewer animals than you would have otherwise. The snaking strategy does work better than random, so you could just do a random strategy, place them wherever. So that's good to know, is that strategy is better than nothing. It's very high effort, though, so it really would be better if they had something that balanced the results of these. Another insight that you can get from this is you can start to look at the graph theoretic properties of the nodes in your graph. And you might guess this actually if you just think about sort of how the disease is spreading and what its properties are. It turns out that the nodes that, if you test across many, many different random graph configurations, the nodes that have a high betweenness centrality, meaning there are more shortest paths that lead through that node than other nodes, those high betweenness nodes also have higher infection probabilities. Because if you imagine the disease popping up at a random point in the graph, it has more of a chance of going through that node as there is more connectivity to that node. And so this actually answers that question that we wanted to know, is if you have high risk or low risk nodes. Yes, it turns out you do, and you can actually measure them without doing anything but having a graph of your system, which is kind of a nice thing to take away. So then I moved on to trying to design a machine design strategy. This, like I said, is still a work in progress. Turns out to be a very, very hard problem, but I used reinforcement learning to do it. I'm happy to dig in after the talk as to why reinforcement learning and not other types of AI learning systems, but this is the basic idea of a reinforcement learning system. The environment is that kennel graph, it's the simulation. The reward in this case is just the infection rate, but you have to be very careful not to give the infection rate with too high a fidelity. The real world people don't know when a node is infected, and so the agent should not know that the node is infected either. The agent should only have access to the information that we have in the real world, not like the full admin access of what's going on in the graph. So the reward is some proxy for what the infection rate is. The state is some masked version of that simulation. Show them the things a human would get to see if they were measuring the simulation. And then the action in this case is that the agent gets to decide how to rearrange the animals within the kennels to minimize the spread of the infection, or where to place new animals when they come into the system. So there are many levels of difficulty in this problem. You can kind of define it in terms of what arbitrary variables you're allowing to change. The most general version of this would be you have an arbitrary graph, any graph, and an arbitrary point in time in the progression of the outbreak within your simulation, and an arbitrary state, meaning any rearrangement of the animals. And then the agent should be able to make an optimal choice, no matter what those different configurations are. I did make the choice, like I said, to make it all planar graphs. You could also lift that restriction. Maybe there's stacked kennels. When you look at it and run a bunch of simulations, letting all these things vary, if you start the simulation from 0 animals, which is not common, but also not entirely uncommon, because oftentimes they'll spin up these intake areas when they start to notice disease in their population, so it sort of starts from 0. You see this sort of common disease saturation curve that'll happen where it asymptotically approaches a particular infection rate, and that infection rate just holds sort of indefinitely in the future. And so that's really what we want to measure, is how well you're doing with that asymptotic infection rate. And you can sort of look over time at what this looks like as it unfolds. You can also restrict the problem a bit, say, okay, we maybe can retrain the algorithm every time there is a new shelter that has an outbreak on their graph of whatever their shelter is. That makes it a little bit easier. We don't have to train on any graph. We can restrict it even further and say, well, maybe we can retrain for halfway through this curve. So we're assuming we're going to get there after 4 days. We don't have to train for this beginning part where we're spinning up the system. They'll take our advice, they'll start the thing, and then we'll come in and start giving them a strategy on day 5, something like that, which also makes the problem easier. And then finally, the problem that I ended up attempting to solve is take all those restrictions and then add on to it the restriction that we're going to take a literal single point in time and a single situation within the graph, which is about as restricted a case as you can have. That's a very, it's borderline not useful to be able to do that. You'd have to retrain the agent basically every day, which is not ideal. But when you do this, it actually turns out to be equivalent to sorting a list of values where the values are probability distributions that you don't know. So you're sampling the values, which is kind of an interesting math observation. So in order to train this thing, you have to have a huge amount of observations. It's a stochastic problem, so that makes it even harder. It's very sensitive to those initial conditions, which makes it a somewhat chaotic system. I haven't proven that. And then there are a lot of edge cases that we know about. For instance, if the graph configuration has all unconnected nodes, the disease doesn't spread. So we know about those. And there's probably a bunch of edge cases we don't know about. So this low-level problem is still really hard, and like I said, is equivalent to sorting sort of a bunch of unknown values, which is a solvable problem, but not easy to solve. And so I took my shot at solving that version of the problem after realizing I wasn't going to solve any of those top ones, and actually was able to train an agent that was able to tie the best human strategy, which in this particular case, I eliminated the room locking because it's sort of cheating. You're allowing yourself to not take in animals, which is not the reality of the situation. And so trained against the snake versus the random and was able to tie. The trick in training this thing is a lot of times it likes to do nothing over doing something. Seemingly that works better. And I think the reason is because it's so easy to do something that makes it worse because of those properties we talked about earlier, which is that if you change the adjacency of two animals, then you're more likely to spread the disease more. And so the actual choices you make have to be very careful and very fine-tuned. So training something like this is not easy. And I think really the limitations here are a lot more computational power. I was just running this on my local computer, and anyone who's done reinforcement learning knows you benefit a lot from being able to run it several million times and not several tens of thousands of times. And then also just sort of a better understanding of some of those other sort of onion layered versions of the problem. So a lot more to talk about there, but let's move on because I've got 10 minutes to go over one more thing, which is this sort of high-level problem-solving oriented approach to how shelters work in general. So shelters in the US, there are about 13,000 known rescues and shelters in the US alone. They serve, we think, somewhere between 6 and 8 million animals a year. Shelters are really just designed to serve as many animals as possible, as efficiently as possible, and they're constantly overwhelmed. And so many of them don't know what data to write down. They don't have time to figure it out. They kind of write down everything or nothing or somewhere in between, more or less at random. And they don't really know the best way of measuring their success and doing so in a way that when they develop a strategy that works for a certain population, like we have with Parvo or with some of these other things, they don't know how to share those solutions with other shelters effectively because they're not all talking the same language in terms of how they're measuring their success. So really, there's no standardization of data, no standardization of KPIs or the ability to create those things and measure their success and then share those ideas. And so as many of you probably are imagining right now, there's lots of ways you can address these problems. You just have to have the time and the know-how to do so. And so the sort of strategies that I took were designing things like critical data templates. So here's the list of 10 things that if you're only going to write down 10 things, write down these 10 things because they're the ones that are going to get you the most answers. Provide recommendations given those 10 things, 4 different metrics they can measure. There's this issue with an idea called Goodhart's law in here, which is that if you give them just sort of a single top-level KPI or even 2, they're going to find ways to min-max those without actually solving the problem. And this is true of every organization. Top-level KPIs are very risky, and they're a good way to trap yourself into bad practices because you want to maximize that number at all costs without actually thinking about your mission. So that's tricky. And then most importantly, provide a tool that allows them to do all these things very easily and then link that tool and its results, when it gives you a result, back to documentation so that other shelters can self-serve on these things and come up with what are their problems and what are their solutions without even needing to reach out to anyone. Make it as fast and easy as possible. So as you can imagine, data templates, there's a bunch of ways to do these. Most of these shelters use various versions of Google tools, and so giving them a template in Google Sheets that allows them to know what all of the critical values are, and if they're categorical, what categorical values that we would recommend they use, and then providing interfaces to common databases that allow them to convert their data into a standardized format. That's the strategy I ended up taking. Standardizing the KPIs, there's a lot of different critical KPIs, and I think actually providing a view into a dozen or so of them is really helpful, as long as those dozen or so abstract out to solution documentation. And so I built actually a first version of the dashboard using a combination of tools that was designed to be able to be spun up and run sort of locally and or to be in a web presence if you're willing to spin up the server-side stuff, and allow them to create these little printable interactive dashboards where they can save a copy of it, distribute it in an HTML file to whoever they want, and link to the documentation as appropriate. So that was the prototype for that. American Pets Alive as an organization is entirely about this problem, and so they were really excited that someone had like a tech thing that would make it easier for them. And so we very quickly prototyped it with 8 different shelters who were able to run their data through it. We found all sorts of different issues with, in particular, cause of death is really the critical thing in there, right? Because you want to save them from that. And most shelters don't have a good way of logging cause of death consistently, so that's still an open problem. We did find after a while people didn't want to deal with sort of local Python or even server Python code maintenance, and so creating a easy to maintain version of this became the next step, which is just basically port all those figures over to a Google cloud version of that using Google Data Studio. This seems to be the preferred solution for many people. It's fairly feature rich. It doesn't scale super well, and if you're like Dallas and you take in 30, 40,000 dogs a year, this doesn't perform super well. It's probably still better than anything that they have right now, but I think there's probably going to be somewhere to meet in the middle between those solutions that's going to work best. As you saw at the beginning, I sort of throw multiple tools at these problems because I know that not all of them are going to stick, and if you put all your eggs in one basket, you're just going to lose. And so then we have documentation for some of these problems. This is the Parvo documentation. It's a public wiki that says literally everything you need to know about how to treat Parvo, so we can link that into there. One thing that we haven't done, though, is add automatic decision-making processes for them to help them find out, diagnose their issues, and then link out to these documents. So we give them sort of the dashboard, and then we give them the list of solutions, but we don't have a good link between the two yet. But the combination of these things, I hope in the coming weeks and months will mean that shelters will be more enabled to self-serve on this problem of how do I serve my population better. Okay, so coming back to the key takeaways, those are the three topics I wanted to talk with you all about, and really as cool as that technology is, the thing I would like you to take away from this talk is all of that stuff was stuff I did in my free time, and I did it for fun, and it was super satisfying and super interesting. And if you find yourself with free time and you want to do a cool tech project, there are so many nonprofits in town that you could help out, and they don't know that they need help. And so you need to reach out to them. If there's an issue that you care about, if there's a problem that you're interested in, find an organization in Austin, find a national organization, reach out to them and offer to help. And they'll say sure, and then you'll have to set up 4 different meetings because they're going to cancel 3 of them. And then eventually you're going to get to where you understand their problem and you can work autonomously on that problem. And you can deliver them 4 tools where they pick one and they'll use it. And honestly, the satisfaction you're going to get out of following something like this is so excellent that I want everyone to do it if they have the time and the interest. I do want to thank some of my collaborators who helped me out with the various projects and some of the data analytics and helping me get the data. And I want to thank you all for your time. So I think we only have a couple minutes for questions, but I'd love to answer any questions you have. Yeah. Data from shelters to data from what? No, so this is something I would love to be able to do. Vet offices are almost always private businesses, and I'm not sure how to get them to give up any data. I actually think a lot of them would be down to do it with the right data use agreements in place to where they feel protected, but there's such a huge financial and liability risk to them. There is for other shelters, but there's more of a standard in, even in private, so APA is a private shelter as opposed to AAC, which is the city-run shelter. The city-run shelter has legal mandates that actually just got passed a month or so ago that they must share data. APA chooses to share data, but it's actually a risk for APA to do that because people like to attack shelters. It's a very hot button issue and everyone loves to attack each other in that space. And so I think private practices would be very reticent to do anything like that, but I would love to do it with them if they'd be interested. Yeah. So I started the Parvo efforts, as in I started pitching it to people and trying to get people interested in it in probably 2014 when I started my PhD. It took maybe 2 years before I got my first piece of data out of that. I built a lot of tools along the way. Actually, that's not true. I built many of the tools I talked about in the very beginning starting in 2011. The moment I got there, I saw they needed a scheduling tool. They needed a end of shift report, those sorts of things. The distemper one I started about a year and a half ago, but I haven't worked on it in several months. The KPIs one, though, I think I only started about 6 months ago. And many of these things I find happen in very quick sprints. Like you start working on it, you make a lot of progress in about a month, 2 months, and then it just sort of goes away for 6 months and then it comes back up. And the key is to be open to it coming back up and not just abandoning something because you're not making progress on it. And if you have enough projects going on at the same time, you're always going to be making progress on something. Mm-hmm.
So have you looked into that, and also if you how did you get the data, and do you have to work with them in order to have accurate input of the data into the system?
Yeah. So on the I'll do the data one first. So the question was, how did you get the data, and did you have to work with them to get accurate data input into a system? So some of the tools that I built, like the end of shift report, are forms that they fill out. And so data accuracy, obviously you're worried about people having an incentive to enter the data accurately. On those, the incentive is actually that every day when people are about to come into the shift, they look at the output of that form, which gets published somewhere, and they say, oh, how long am I going to have to expect to be on this volunteer shift? So everyone who uses that particular data entry mechanism also is incentivized to look at the results, which creates a nice closed loop incentive for them to enter accurate data. On the treatment sheet side, I actually do think the data accuracy could improve, because those, you're taking that, I think I showed it at some point, an image of a treatment sheet and then inputting rows for every column that's in that treatment sheet. And we actually were able to get funding after a little bit to hire a new veterinary technician who, in their free time, while they were doing their normal vet tech work, spent time doing data entry on those things. We actually now have a big data set of pictures of those treatment sheets, and I think it'd be awesome to have a computer vision approach to automatically input those, so that if there are biases in our input approach, at least they're consistent, because humans are very inconsistent, or to otherwise crowdsource the entry of that information. I think we can do a lot better on that front. And as we collect more and more data, 800 samples a year, we already have the biggest parvo data set in the world. We're going to have the biggest by 2 orders of magnitude soon. And so I think that would be great. On the cats issue, the article that I linked to earlier, I actually highlight the disparity between cats and dogs and how we talk about them and culturally within the shelter system in that article. If you look at like a Google search frequency for dog adoption versus cat adoption, cats are at like a third consistently of searches for dogs. If you look at adoption records, you find that people who adopt cats are way more likely to adopt a second cat. People who adopt dogs are more likely to just adopt one. There's a lot of asymmetries in that system. For these diseases, distemper does not have a great analog for cats, but parvo does. It's called panluc. And we actually in the parvo ICU treat both. So we have kittens who come in with panluc and we treat them. And we haven't looked a lot at the data yet, so I do think there's a lot of cool openings to do that. We are working on a study right now on animal bonding specifically in cats, and cats that have particular conditions like paralysis or diabetes that requires a lot of maintenance. Does that create a tighter bond with their owner? So I think there's a lot of unique problems in cats that we're starting to try to address, but there's a weird cultural asymmetry in how much effort we put into cats versus how much effort we put into dogs that I don't think anyone's quite gotten their head around yet. So now we're out of time. I don't know if we have time for one more question. Are there any one more question maybe? Nope. Okay. Thank you very much.